Tonight we're going to explore something that most people think they understand, but almost nobody truly does. The speed of light. You've heard it 1,000 times, nothing can travel faster than light. But here's what almost everyone gets wrong. The universe doesn't have a speed limit because light happens to be fast. Light travels at that speed because the universe has a speed limit. That's a completely different statement, and understanding the difference will change how you see everything. Because this limit isn't a rule imposed on objects moving through space. It's something far deeper. It's built into the very fabric of reality itself. It's the reason cause comes before effect. The reason time moves forward. The reason you exist at all. And by the end of tonight, you're going to understand exactly why. Before we go any further, if this kind of deep exploration is something you enjoy, a quick like or subscribe really helps the channel more than you might think. It's a small thing, but it genuinely makes a difference. Now, let's begin. Let's start with something you do every single day without thinking about it. You move, you walk across a room, you drive down a street, you throw a ball to a friend. Motion is one of the most basic, most familiar things in your experience. You understand speed intuitively. You know that a car going 60 miles per hour is faster than one going 30. You know that if you're on a train moving 50 miles per hour and you walk toward the front of the train at 3 miles per hour, someone standing on the platform watching you pass would see you moving at 53 miles per hour. The speeds add up. It's obvious. It's common sense. It's how the world works. This simple addition of speeds is something you've relied on your entire life without ever questioning it. If you're on a boat moving 10 miles per hour down a river, and you throw a ball forward at 20 miles per hour, someone on the shore sees the ball moving at 30 miles per hour. The ball's speed plus the boat's speed equals the total speed as seen from the shore. This works every time. It works for cars, for planes, for people walking on moving sidewalks in airports. It works for runners passing a baton in a relay race. It works for a child throwing a paper airplane from the back seat of a moving car. It works for everything you've ever experienced in your daily life. And for thousands of years, nobody had any reason to think it wouldn't work for everything in the universe. Isaac Newton formalized this idea in the 17th century. His laws of motion described a universe where space was absolute, time was absolute, and velocities simply added together. This framework, called Galilean relativity, worked beautifully. It predicted the motion of cannonballs and planets, pendulums and tides. It described the physical world with stunning precision. Engineers used it to build bridges and machines. Astronomers used it to predict eclipses and the paths of comets. For over 200 years, Newtonian mechanics was the unquestioned foundation of physics. It seemed complete. It seemed perfect. It seemed like the final word on how motion works, but it wasn't, because there is something in this universe that breaks this rule completely. Something that refuses to follow the simple addition of speeds that governs everything else, and that something is light. Before we can understand why light is special, we need to understand what people thought about light for most of human history. For a very long time, virtually everyone assumed that light traveled instantaneously. You open your eyes and you see. You light a candle and the room is bright. There's no delay, no waiting. Light just appears. The ancient Greeks debated the nature of light extensively. Some, like Empedocles, believed light had a finite speed. He argued that light must travel from the sun to Earth, and that this journey must take time even if it was too fast to perceive. Others, including Aristotle, argued that light was instantaneous. Aristotle believed that light was not something that moved through space, but rather a state, a condition of the medium between the eye and the object. His view dominated for nearly 2,000 years, mostly because everyday experience seemed to confirm it. When you light a lamp, you don't see the light creep across the room. It's just there, everywhere at once, instantaneous. And honestly, if you think about it, that's a perfectly reasonable conclusion based on the evidence available. If light has a speed, it's so fast that no human experiment in the ancient world could have measured it. You can't stand on a hilltop, flash a lantern, and time how long it takes someone on another hilltop to see it. The delay is far too small. Galileo actually tried this experiment in the early 1600s. He and an assistant stood on two hills, about a mile apart in the Tuscan countryside, each holding a covered lantern. Galileo would uncover his lantern, and when the assistant saw the flash, he would uncover his own. Galileo would then try to measure the time between uncovering his lantern and seeing the flash from the assistant's lantern. The result was inconclusive. The delay, if there was one, was too short to measure, lost entirely within human reaction time. Galileo concluded that light was either instantaneous or extremely fast. He was right about the second part. Light crosses a mile in about 5 millionths of a second. No human could ever hope to measure that with a lantern and a stopwatch. The first real measurement of light speed came from an unexpected place, not from a laboratory on Earth, but from watching the moons of Jupiter. In 1676, a Danish astronomer named Ole Rømer was working at the Royal Observatory in Paris, studying Io, one of Jupiter's 4 large moons, discovered by Galileo decades earlier. Io orbits Jupiter in a regular pattern, disappearing behind the giant planet at predictable intervals of about 42.5 hours. Rømer was timing these eclipses carefully over many months, and he noticed something strange. The timing of Io's eclipses varied depending on where Earth was in its orbit around the Sun. When Earth was closer to Jupiter, moving toward it in its orbit, the eclipses happened slightly earlier than predicted. When Earth was farther from Jupiter, moving away from it, they happened slightly later. Over the course of several months, the discrepancy accumulated to about 22 minutes. Rømer realized what was happening. It wasn't that Io's orbit was changing. Io was doing exactly what it always did, circling Jupiter with clockwork regularity. The difference was that light from Jupiter took time to reach Earth. When Earth was closer to Jupiter, the light had less distance to travel, so it arrived sooner. When Earth was farther away, the light had to travel a greater distance, so it arrived later. The difference in timing corresponded to the extra distance light had across as Earth moved in its orbit. From this observation, Rømer calculated that light took about 22 minutes to cross the diameter of Earth's orbit around the Sun. His number wasn't quite right. The actual value is closer to 16 minutes and 40 seconds. His error came from not knowing the exact size of Earth's orbit, which wouldn't be precisely measured for another century. But the principle was correct and revolutionary. Light was not instantaneous. It had a finite speed. It took time to travel from one place to another. This was a fundamental shift in understanding. For the first time, humanity had solid evidence that light was not magic, not instantaneous, but a physical phenomenon that moved at a finite, measurable velocity. Something that took actual time to cross actual distances. Over the following centuries, the measurement of light speed became more and more precise. In 1849, the French physicist Hippolyte Fizeau conducted the first successful measurement of the speed of light entirely on Earth's surface. He set up a rapidly rotating toothed wheel and shone a beam of light through the gaps between the teeth. The light traveled to a mirror about 5 miles away and bounced back. If the wheel was spinning at just the right speed, the returning light would pass through the next gap in the wheel and reach the observer. If it was spinning too fast or too slow, the light would be blocked by a tooth. By carefully adjusting the rotation speed of the wheel and noting when the returning light appeared brightest, Fizeau could calculate how long it took light to make the round trip. And from that, he determined its speed. Fizeau's result was remarkably close to the modern value, about 313,000 kilometers per second. Not perfect, but within 5% of what we know today. In 1862, Léon Foucault improved on this using rotating mirrors. Instead of a toothed wheel, getting an even more precise value of about 298,000 kilometers per second. Each new experiment refined the number further. By the late 1900s, we had pinned down the speed of light with extraordinary precision, using lasers and atomic clocks. The exact value is 299,792.458 kilometers per second. In 1983, this measurement became so precise that scientists actually redefined the meter based on it. 1 meter is now officially defined as the distance light travels in one 299,792,458ths of a second. The speed of light became exact by definition, and the meter adjusts to match. So by the late 1800s, scientists knew the speed of light very precisely. But knowing how fast light travels was just the beginning. The truly revolutionary discovery was still to come, and it started with a question that seemed simple at the time but turned out to be one of the most important questions in the history of physics. The question was this: the speed of light relative to what? Think about that for a moment. When you say a car is moving at 60 miles per hour, you mean 60 miles per hour relative to the ground. When you say a ball is moving at 20 miles per hour, you mean relative to the person who threw it, or relative to the ground, or relative to whatever reference point you choose. All speeds are measured relative to something. There's no such thing as an absolute speed without a reference frame. So when scientists said light travels at about 300,000 kilometers per second, the natural question was relative to what? In the 1800s, most physicists believed the answer was the ether, the luminiferous ether. This was a hypothetical substance that was supposed to fill all of space, permeating everything, occupying every corner of the universe. Light, they believed, was a wave, similar to sound, and sound waves need a medium to travel through. Sound moves through air by causing air molecules to vibrate. It can also travel through water and solid materials, but sound can't travel through a vacuum because there's nothing to vibrate. Since light clearly can travel through the vacuum of space, reaching us from the sun and distant stars across millions and billions of miles of emptiness, physicists reasoned that there must be some invisible medium filling that space. Something for light waves to vibrate in. They called this medium the ether. It was supposed to be perfectly transparent, perfectly stationary, filling the entire universe like an invisible ocean through which everything moved. If the ether existed, then the speed of light would be measured relative to this ether, just as the speed of sound is measured relative to the air. And that meant Earth's motion through the ether should be detectable. As Earth orbits the sun at about 30 kilometers per second, It should be plowing through the ether like a boat through water. Light traveling in the same direction as Earth's motion should appear to move slightly slower relative to us, like swimming against a current. Light traveling in the opposite direction should appear slightly faster, like swimming with the current. And light traveling perpendicular to Earth's motion should be somewhere in between. The differences will be small, fractions of a percent, but with precise enough instruments, they should be measurable. In 1887, two American physicists, Albert Michelson and Edward Morley, set out to measure this difference. Their experiment, conducted at what is now Case Western Reserve University in Cleveland, Ohio, was elegant and precise. They built a device called an interferometer that split a beam of light into two paths at right angles to each other. One beam traveled in the direction of Earth's presumed motion through the ether, and the other traveled perpendicular to it. Both beams were reflected back by mirrors and recombined at a detector. If Earth's motion through the ether affected the speed of light differently in the two directions, the two beams would be slightly out of step when they recombined, producing a detectable shift in the interference pattern. The expected shift was small, but well within the instrument's capability to detect. Michelson and Morley expected to see this shift change as they rotated their apparatus to different orientations relative to Earth's motion. They took extraordinary care to eliminate vibrations and other sources of error. They mounted the entire apparatus on a massive stone slab floating in a pool of mercury so it could be rotated smoothly without any jolts or tremors. They repeated the measurements at different times of day. When Earth's rotation would point the apparatus in different directions, they repeated them at different times of year when Earth would be moving in different directions along its orbit around the Sun. The result was nothing. No shift, no difference. No matter which direction they pointed the apparatus, no matter what time of day or what season, the speed of light was exactly the same in every direction. Earth's motion through space had absolutely no effect on the measured speed of light. The ether wind they expected to find simply wasn't there. This was one of the most famous null results in the history of science. Michelson and Morley had built one of the most precise optical instruments of the 19th century, sensitive enough to detect changes far smaller than what they expected, and found absolutely nothing. At the time, many physicists considered the experiment a failure. They had expected to detect the ether and hadn't. Something must be wrong with the experiment, or something must be hiding the result. Various explanations were proposed. Maybe the ether was being dragged along with Earth, like air inside a moving car, so there was no relative motion to detect. Maybe objects moving through the ether physically contracted in the direction of motion, exactly enough to cancel out the expected effect. And then the Dutch physicist Hendrik Lorentz and the Irish physicist George Fitzgerald independently proposed that objects physically shorten in the direction of their motion through the ether. This length contraction, they argued, would perfectly compensate for the expected time difference, explaining why Michelson and Morley couldn't detect the ether wind. Lorentz even developed a full set of mathematical equations, now called the Lorentz transformations, that described exactly how much objects would contract and how time would slow down to maintain the illusion that light speed was constant. These were clever ideas, but they were also desperate patches. They were trying to save the ether by adding more and more assumptions, each one designed specifically to explain why the ether couldn't be detected. The ether was becoming increasingly invisible, increasingly undetectable, increasingly indistinguishable from something that simply didn't exist. The explanations were getting more complicated while explaining less and less. And then, in 1905, a 26-year-old patent clerk in Bern, Switzerland, proposed something radical, something that swept away the ether, the patches, the complications, and replaced them all with a single breathtaking idea. Albert Einstein didn't try to explain why the ether couldn't be detected. He simply proposed that there was no ether. That light didn't need a medium to travel through. Light was perfectly capable of moving through empty space with nothing to vibrate in. And then he went further. He proposed two postulates. First, the laws of physics are the same in all inertial reference frames, meaning in all frames of reference, moving at constant velocity. Second, and this was the revolutionary one, the speed of light in a vacuum is the same for every observer, regardless of how fast they're moving or how fast the light source is moving. Read that second postulate again, because it's the key to everything that follows. The speed of light is the same for every observer, regardless of how fast they're moving. This sounds absurd. It contradicts everything you know from daily experience. If you're on a train moving at half the speed of light, and you shine a flashlight forward, you would expect someone standing on the platform to see the light moving at 1.5 times the speed of light. That's how speeds work, right? You add them. The train speed plus the light speed should equal the total speed as seen from the platform. But Einstein said no. The person on the platform sees the light moving at exactly the speed of light. Not 1.5 times, just the speed of light. The same speed you measure on the train. The same speed everyone measures. Everywhere, always, no matter how they're moving. And here's what makes this even more bewildering. It's not just the person on the platform. You on the train also measure the light moving at the speed of light relative to you. Both observers, moving at different speeds relative to each other, both measure the exact same speed for the same beam of light. This seems impossible. If you and I are moving relative to each other, how can we both measure the same speed for the same object? In our everyday experience, this never happens. If I'm standing still and a ball passes me at 20 miles per hour, and you're running alongside the ball at 10 miles per hour, you'll measure the ball as moving at only 10 miles per hour relative to you. We get different speeds, which makes sense because we're moving at different speeds ourselves. But light doesn't work that way. Light insists on being measured at the same speed by everyone. No matter how fast you're moving, no matter what direction, no matter where you are in the universe, when you measure the speed of light, you always get the same answer. 299,792.458 kilometers per second. Always. Without exception. This has been confirmed by every experiment ever performed. Not once, in over a century of testing with increasingly precise instruments, has anyone found the speed of light to vary depending on the motion of the observer or the motion of the source. Now, Einstein realized something that most people miss when they first hear this. If the speed of light is the same for everyone, then something else has to give, because the mathematics simply doesn't work otherwise. Speed is distance divided by time. If two people moving at different speeds both measure the same speed for a beam of light, and they agree on the speed, then they must disagree about the distance and the time. They must measure different distances, or different times, or both. And that's exactly what Einstein showed. If the speed of light is constant for all observers, then space and time themselves must be flexible. They must change depending on how fast you're moving. Time must pass at different rates for observers moving at different speeds. Distances must change depending on the observer's motion. Even the simultaneity of events, where the two things happen at the same time, must depend on your state of motion. Two events that are simultaneous for one observer might happen at different times for another observer moving at a different speed. This was Einstein's special theory of relativity, published in 1905, and it shattered the Newtonian understanding of the universe that had held for over 2 centuries. Space and time were not fixed, rigid, absolute things that formed a static stage on which events played out. They were malleable, relative, dependent on the observer's motion. The only thing that was absolute, the only thing that was the same for everyone, regardless of how they moved, was the speed of light. Let me make this concrete. Imagine you're standing on a platform watching a train go past at a significant fraction of the speed of light. On the train, a passenger has set up a simple light clock. There's a light on the floor that sends a pulse straight up to a mirror on the ceiling and back down again. The passenger measures the time it takes for the light to make this round trip and uses it as a clock. Each tick of the clock is one round trip of the light pulse. From the passenger's perspective, the light goes straight up and straight down. Simple. The distance is just twice the height of the train car. But from your perspective on the platform, the train is moving. So the light doesn't go straight up and straight down. It goes up and to the right as the train moves, hits the mirror, then comes down and to the right. From your perspective, the light traces a longer diagonal path, a zigzag instead of a straight vertical line. Here's where it gets strange. The speed of light is the same for both of you. The passenger on the train and you on the platform both measure the light pulse traveling at exactly the same speed. But from your perspective, the light has to travel a longer distance because it's following a diagonal path. If the speed is the same but the distance is longer, then the time must be longer. From your perspective, the passenger's clock is ticking more slowly than yours. Time is literally passing more slowly on the moving train, as measured by you. This isn't a trick. It's not an illusion or a problem with measurement or a flaw in the clock. Time itself is passing at a different rate. The passenger's heart beats more slowly. Their thoughts proceed more slowly. Every chemical reaction, every biological process, every physical process on that train happens more slowly from your perspective on the platform. But from the passenger's perspective, everything on the train seems perfectly normal. Their clock ticks at the normal rate. Their heart beats normally. It's your clock, back on the platform, that seems to be running fast. Both perspectives are equally valid. There's no cosmic referee who can say which one is right and which one is wrong. They're both right. Time is relative. It depends on your motion. This idea was so radical in 1905 that many physicists simply didn't believe it. It went against everything that Newton had established, everything that seemed obviously true about the world. Time was supposed to be universal. 1 second was 1 second for everyone, everywhere, always. The idea that time could pass at different rates depending on how fast you were moving seemed like madness. But here's the thing. Einstein was right. Every single prediction of special relativity has been confirmed by experiment. Time dilation is real. We've measured it directly. We've confirmed it with atomic clocks flown on airplanes, an experiment we'll look at in detail shortly. We've confirmed it with particles moving at nearly the speed of light in accelerators. We rely on it every single day without knowing it because the GPS satellites orbiting Earth move fast enough and sit high enough in Earth's gravitational field that relativistic time corrections are essential. Without those corrections, your GPS position would drift by about 10 kilometers within a single day. The fact that your phone can navigate you to a restaurant is proof that Einstein was right about time. The speed of light isn't just fast. It's not just a really big number that describes how quickly a beam of light gets from one place to another. It's a fundamental constant of the universe, woven into the structure of reality itself. And the fact that it's the same for everyone, that it refuses to behave like every other speed we've ever experienced, is the first clue that something profoundly deep is going on, something that goes far beyond just how fast photons travel. What Römer discovered in 1676 was that light has a finite speed. What Michelson and Morley discovered in 1887 was that this speed doesn't change based on the observer's motion. What Einstein understood in 1905 was what these facts truly meant. Not just for light, but for space, for time, and for the very architecture of the universe. Because when Einstein showed that the speed of light is the same for all observers, he wasn't just making a statement about light. He was revealing something about the deep structure of space-time itself. The speed of light is not merely the speed of a particular thing moving through space. It is the speed at which causality propagates. It is the maximum rate at which any information, any influence, any cause can produce an effect anywhere else in the universe. And this speed limit isn't imposed on the universe from the outside like a rule posted on a highway. It's part of the geometry of space-time itself. It's built in. It emerges from the very shape of reality. But to understand why that's true, we need to go deeper. We need to look at what space-time actually is, and why its geometry demands that a maximum speed exists. And that's where things get truly mind-bending. Because the speed limit isn't really about speed at all. It's about the shape of reality itself. Understanding this requires us to abandon one more assumption we carry from everyday life. We think of space and time as time. Two completely separate things. Space is where things are. Time is when things happen. They seem like entirely different concepts, as different as color and temperature. You can move freely through space in any direction, left, right, forward, backward, up, down. But time seems to flow in only one direction, forward, at a steady rate that you cannot control. Einstein showed that this separation is an illusion. Space and time are not separate entities. They are aspects of a single unified fabric called space-time. And the speed of light is the thread that stitches them together. It's the conversion factor between spatial distance and temporal duration, the constant that tells you how much of one equals how much of the other. This isn't just a mathematical convenience or a clever way of thinking about things. Space-time is physically real. It's the arena in which everything in the universe exists, and everything that happens takes place. And the speed of light isn't just the speed at which photons happen to travel. It's a structural feature of this arena, embedded in its geometry from the very beginning. Understanding that geometry is the key to understanding why the universe has a speed limit at all. To understand why the universe has a speed limit, you need to understand something about the nature of reality that is genuinely strange. Something that goes against every intuition you've developed from living in the world. And it starts with a question that sounds almost philosophical. What is space? What is time? And are they really what they seem to be? In your everyday life, space and time feel like completely different things. Space is the stage. It's the room you're sitting in, the distance between your house and the grocery store, the gap between Earth and the moon. You can move through space in any direction. You can go left or right, forward or backward, up or down. You have freedom to move through space however you choose. Time, on the other hand, feels nothing like space. Time flows. It ticks forward, 1 second after another, relentlessly, unstoppably. You can't turn around in time, you can't go backward, you can't choose to move through time faster or slower. Time just happens to you. You're carried along by it like a leaf on a river, unable to swim upstream, unable to stop, unable to do anything but drift forward at whatever pace the current dictates. This distinction between space and time seems so obvious that for most of human history, nobody seriously questioned it. Space was space. Time was time. They were separate things, unrelated categories of existence. Newton built his entire framework on this assumption. In Newton's universe, space was a fixed, rigid, three-dimensional grid that extended infinitely in all directions. Time was a separate, universal clock that ticked at the same rate everywhere, for everyone, always. Objects moved through space as time ticked along, but space and time themselves were independent of each other and independent of whatever was happening inside them. But Einstein showed that this picture is wrong. Space and time are not separate. They are woven together into a single four-dimensional fabric that physicists call spacetime. This isn't a metaphor. It isn't poetry. It's a precise mathematical statement about the structure of reality. Space and time are connected, intertwined, mixed together in a way that becomes apparent only when things move at speeds approaching the speed of light. At the slow speeds of everyday human experience, walking, driving, even flying in an airplane, the connection between space and time is so subtle that it's completely undetectable. Space looks like space. Time looks like time. Everything seems separate and independent. But at high speeds, the connection reveals itself. Space and time start to blend into each other. Moving through space affects how you move through time. And this blending is not a minor effect. It's fundamental. It's the reason the speed limit exists. Let me try to explain this in a way that makes intuitive sense, because this is the key concept. The heart of why a maximum speed exists in the universe. Imagine you're driving a car on a large, flat, open plain. No roads, no obstacles, just flat ground in every direction. You're driving at exactly 100 miles per hour. That's your total speed. It doesn't change. Your speedometer is locked at 100. Now you can choose what direction to drive. You can drive due north. If you do, all 100 miles per hour of your speed is taking you northward. You're covering 100 miles of northward distance every hour. Your eastward speed is 0. All your motion is in the north direction. But now, suppose you turn your steering wheel and start driving northeast. You're still going 100 miles per hour. That hasn't changed. But now your speed is split between two directions. Some of it is taking you north, and some of it is taking you east. If you're driving at a 45-degree angle, roughly 71 miles per hour is carrying you north, and 71 miles per hour is carrying you east. Your total speed is still 100 miles per hour, but your northward speed has decreased because some of your motion is now going east. The more you turn toward the east, the less of your speed goes north. If you turn all the way and drive due east, all 100 miles per hour is taking you eastward, and your northward speed is 0. You haven't slowed down. You're still going 100 miles per hour, but you've rotated your direction of motion so that none of it points north anymore. This is a simple idea. Your total speed is fixed, and you can rotate it between different directions. More speed in one direction means less speed in another. The total always stays the same. Now, here's the mind-bending part. This is almost exactly how space-time works. Except instead of north and east, the two directions are space and time. Everything in the universe, every object, every particle, every atom is always moving through space-time at exactly the same total rate. This rate is the speed of light. Always. Without exception. You, sitting in your chair right now, reading these words, are moving through space-time at the speed of light. A rocket ship hurtling through space at 90% of light speed is moving through space-time at the speed of light. A beam of light itself is moving through space-time at the speed of light. Everything moves through space-time at the same total rate. That rate is fixed. It cannot be changed. It is a fundamental constant of the universe. What changes is the direction of that motion through space-time. And this is where the speed limit comes from. When you're sitting still, not moving through space at all of your motion through space-time is directed through time. You're moving through time at the maximum possible rate. 1 second per second, as measured by your own clock. All of your space-time speed is being used up moving you forward through time. But when you start moving through space, something has to give, because your total speed through space-time is fixed. It's always the speed of light. So if some of your motion is now directed through space, less of it can be directed through time. Moving through space costs you speed through time. The faster you move through space, the slower you move through time. This is time dilation, not as a strange side effect of some arbitrary rule, but as a simple geometric consequence of how space-time works. Your total speed through space-time is fixed. If you redirect some of that speed from the time direction to the space direction, you have less speed left over for time. Time slows down for you. Not because something is wrong, not because clocks malfunction, but because you've rotated your direction of motion through space-time. Think back to the car analogy. When you were driving due north at 100 miles per hour, all your speed was going north. When you turned to the northeast, some of your speed went east instead, and your northward speed decreased. Nobody would find that surprising. It's just geometry. The total speed stays the same. Turning in one direction means less speed in the other. Space-time works the same way. Moving through space means less movement through time. The faster you go through space, the slower you go through time. And there's a maximum amount of speed available because your total space-time speed is fixed at the speed of light. You can't exceed the speed of light through space, for the same reason you can't drive north faster than 100 miles per hour, when your speedometer is locked at 100. There's simply no more speed available. You've already used all of it. Now, what happens when you reach the speed of light through space? You've rotated all of your space-time motion from the time direction into the space direction. All of your speed is now going through space, and none of it is going through time. This means time has stopped for you. From your perspective, no time passes at all. This is exactly what happens to photons. A photon, a particle of light, moves through space at the speed of light. And from the photon's perspective, time does not pass. A photon emitted from a star 1 billion light years away and absorbed by your eye has experienced 0 time. In the photon's own frame of reference, its emission and absorption happen at the same instant. The entire journey across 1 billion light years of space takes exactly 0 time from the photon's perspective. This sounds impossible, but it's a direct consequence of the geometry of spacetime. This is why nothing with mass can reach the speed of light. To reach light speed through space, you'd need to redirect all of your spacetime motion into the space direction, leaving nothing for time. But objects with mass always experience time. They always have some motion through the time direction. You can redirect more and more of your spacetime speed into the space direction by accelerating, but you can never redirect all of it. You can get asymptotically close, approaching the speed of light through space, with time slowing down more and more, but you can never quite reach it. There's always a tiny bit of motion through time left over. Only massless particles like photons can travel entirely through space, with no motion through time at all. This is not a technological limitation. It's not that we haven't built engines powerful enough yet. It's not that we need better fuel or smarter engineering. It's a geometric fact about the structure of spacetime. Asking why you can't exceed the speed of light is like asking why you can't go farther north than the North Pole. There's no wall at the North Pole blocking your path. There's no fence, no barrier, no sign that says you can't go farther. You can't go farther north than the North Pole because north simply doesn't exist beyond that point. You've reached the maximum of what northness means. Beyond the pole, every direction is south. The concept of north has been exhausted. The speed of light is the North Pole of velocity. It's not a wall. It's not a barrier. It's the point where the concept of moving faster through space has been exhausted. All of your space-time motion is already pointed in the space direction. There's nothing left to redirect. The speed of light isn't a limit imposed on the universe. It's a structural feature of the geometry of space-time. It couldn't be any different, any more than the North Pole could be in a different place on a sphere. Now, I want to be careful here because the analogy between space-time and a car driving on a plane isn't perfect. There's a crucial difference that makes space-time fundamentally different from ordinary space, and understanding this difference is important. In ordinary space, if you have a fixed total speed, and you split it between north and east, you use the Pythagorean theorem to figure out how the components relate. If your northward speed is 71 miles per hour, and your eastward speed is 71 miles per hour, the total is 100 miles per hour. The squares add up. 71 squared plus 71 squared equals 10,000, roughly, and the square root of 10,000 is 100. In space-time, the geometry is different. Space and time don't combine using the Pythagorean theorem. They combine using what physicists call a Minkowski metric, named after Hermann Minkowski, Einstein's former mathematics professor, who realized in 1908 that Einstein's theory could be beautifully understood as geometry in 4 dimensions. In Minkowski's geometry, space and time combine with a crucial minus sign. Instead of adding the squares of space and time components, you subtract one from the other. This might sound like a minor technical detail, but it's actually the most important thing about space-time. That minus sign is what makes time different from space. It's the reason time flows in one direction. It's the reason cause and effect work the way they do. And it's the reason there's a speed limit at all. In ordinary geometry, all directions are equivalent. North is no more special than east. You can rotate freely between them. But in space-time geometry, because of that minus sign, the time direction and the space directions are fundamentally different. You can trade motion through time for motion through space, but you can't do it freely and without consequence. The minus sign creates an asymmetry. It divides all possible directions of motion through space-time into two categories: time-like directions, where more of your motion is through time than through space, and space-like directions, where more of your motion is through space than through time. And right at the boundary between these two categories, perfectly balanced between space and time, are the light-like directions. These are the paths that light follows. They represent the exact dividing line between the time-like and space-like regions of space-time. This is why the speed of light is special. It's not special because light happens to go fast. It's special because it sits at the geometric boundary between two fundamentally different regions of space-time. The time-like region, where objects with mass live and experience the passage of time, and the space-like region, which nothing with mass can enter. The speed of light is the boundary, the dividing line, the edge. Let me try another analogy to make this clearer. Think about the surface of Earth. The equator is a line that divides the planet into two hemispheres, the northern hemisphere and the southern hemisphere. The equator isn't a wall. It isn't a barrier. You can cross it freely. But it is a meaningful boundary. It's the line where latitude changes from north to south. And if someone asked you why the equator is where it is, the answer would be that it's determined by the geometry of the sphere. The equator has to be at the widest part of the planet, halfway between the poles. It couldn't be anywhere else. Its position is a consequence of the shape of Earth. The speed of light is similar. It's a boundary determined by the geometry of space-time. It's the dividing line between time-like and space-like, between the region where causal connections are possible and the region where they're not. And it couldn't be anywhere else, in the sense that any universe with space-time geometry of this type must have a maximum speed. The specific value, 299,792.458 kilometers per second, depends on the particular relationship between space and time in our universe. But the existence of a maximum speed doesn't. Any space-time with a Minkowski-type geometry automatically has a speed limit. It's built into the mathematics. This is why physicists say the speed of light is not really about light at all. Light just happens to travel at this speed because photons are massless, and massless particles must travel at the boundary speed. If light didn't exist, if photons somehow weren't a thing, the speed limit would still be there. It's a property of space-time, not a property of light. Light obeys the speed limit. It doesn't create it. This understanding also explains something that puzzles many people when they first learn about relativity. If the speed of light is the maximum speed, why does it have the particular value it has? Why 299,792 kilometers per second and not some other number? Why not faster? Why not slower? The answer is that the speed of light is really a conversion factor. It tells you how much space corresponds to how much time. It tells you how many meters of space equal 1 second of time in the geometry of space-time. Specifically, 1 second of time corresponds to 299,792,458 meters of space. That's the exchange rate. That's how much space and time are worth relative to each other in the currency of space-time. In some sense, the speed of light isn't even a speed at all. It's a unit conversion. It's like the factor that converts between inches and centimeters, or between pounds and kilograms. Those conversion factors tell you how two different units of measurement relate to each other. The speed of light tells you how the unit of space, the meter, relates to the unit of time, the second. If we measured space and time in the same units, if we measured distance in light seconds, for example, then the speed of light would simply be one light second per second. It's only because we use different units for space and time, meters for one and seconds for the other, that the speed of light appears as a large number. The large number is an artifact of our choice of units, not a statement about the universe. This is a deep insight. The speed of light isn't a property of light, and it isn't really a speed. It's a property of space-time. It's the ratio between space and time. It tells you how the universe converts between distance and duration. And it's the reason that nothing can travel faster than a certain rate, because that rate represents the complete conversion of temporal motion into spatial motion. Beyond that, there's nothing left to convert. Now, let me address something that might be nagging at you. If everything moves through space-time at the speed of light, does that mean we're all moving at light speed right now? In a sense, yes. But you need to be careful about what that means. Right now, sitting still, you're moving through space-time at the speed of light. But almost all of that motion is through time, not through space. You're hurtling into the future at the maximum rate, 1 second per second. From your own frame of reference, you're always moving through time at this rate when you're at rest in space. The only way to slow down your motion through time is to start moving through space. And even then, at everyday speeds, the effect is almost undetectable. If you're walking at 5 kilometers per hour, the fraction of your space-time speed that's being redirected from time to space is so tiny that the time dilation effect is something like 1 part in 10 quadrillion. You'd need to walk for billions of years for the time difference to add up to even a single second. This is why relativity seemed invisible for so long. At human speeds, the mixing of space and time is so slight that it's completely undetectable without extraordinarily precise instruments. Newton's picture of absolute space and absolute time works perfectly well for everyday life, because at everyday speeds, space and time barely interact. It's only when things start moving at a significant fraction of the speed of light that the connection between space and time becomes apparent. That the trade-off between spatial motion and temporal motion becomes noticeable, that the geometry of space-time reveals itself. But just because the effect is small at everyday speeds doesn't mean it isn't there. It is there, always, in every motion you make. Every time you take a step, you're very, very slightly slowing down your passage through time compared to someone standing still. The effect is immeasurably small, but it's real. The geometry of space-time operates at all scales, all speeds, all times. We just don't notice it because we live our lives moving at a tiny fraction of the speed of light. Let me push this understanding a little further. The fact that space-time has this geometry with a maximum speed built into it has consequences that go far beyond just limiting how fast things can travel. It shapes the entire structure of physics. It determines how forces work, how particles interact, how energy and momentum are related. Every fundamental theory in modern physics, quantum mechanics, quantum field theory, the standard model of particle physics, all of it is built on the foundation of space-time geometry. All of it respects the speed limit, not because physicists chose to impose it, but because the mathematics of space-time requires it. For example, consider electromagnetism. The force between electric charges, the way magnets work, the behavior of radio waves, all of this is described by Maxwell's equations, formulated by James Clerk Maxwell in the 1860s. When Maxwell wrote down his equations, he discovered something remarkable. The equations predicted the existence of electromagnetic waves. Waves of oscillating electric and magnetic fields that propagate through space. And the equations predicted the speed of these waves. It wasn't a number Maxwell put in by hand. It emerged naturally from the equations themselves, from the fundamental constants describing the strength of electric and magnetic forces. And the speed that emerged was the speed of light. Exactly. This was how Maxwell realized that light is an electromagnetic wave. The speed of light wasn't a separate fact about the universe. It was a consequence of the fundamental properties of electricity and magnetism. It fell out of the equations naturally. And when Einstein later showed that this speed is a structural feature of space-time, the connection became even deeper. Maxwell's equations aren't just about light. They're about space-time. The speed that emerges from them is the conversion factor between space and time, the fundamental constant of space-time geometry. Electromagnetism obeys the speed limit because it exists within space-time, and space-time has that geometry. The same is true for gravity. In Newton's original theory, gravity acted instantaneously across any distance. If the sun suddenly vanished, Newton's theory predicted that Earth would immediately fly off in a straight line, responding to the loss of the sun's gravity at the same instant it happened, even though the sun is 8 light minutes away. But this can't be right in a universe with a speed limit. If information can't travel faster than light, then the gravitational effect of the sun vanishing can't reach Earth faster than light either. Einstein solved this problem with his general theory of relativity, published in 1915. In general relativity, gravity isn't a force at all. It's the curvature of space-time. Massive objects like the sun curve the space-time around them, and other objects follow the curves. When the sun vanishes in this new framework, the change in space-time curvature propagates outward at the speed of light. Earth wouldn't notice the sun was gone for 8 minutes and 20 seconds, exactly the time it takes light to travel from the sun to Earth. Gravitational information respects the speed limit because gravity is space-time, and space-time has the speed limit built into its geometry. The ripples in space-time caused by massive events like colliding black holes travel at exactly the speed of light. We've detected these ripples. They're called gravitational waves, and they were first directly observed in 2015 by the LIGO experiment. These waves traveled across billions of light years of space at exactly the speed of light, confirming that gravity respects the same speed limit as everything else. Even at the quantum level, the speed limit holds. Quantum field theory, which describes the behavior of fundamental particles and forces, is built on a foundation called Lorentz invariance. This is a mathematical expression of the fact that the laws of physics look the same to all observers regardless of their motion, which is really just a fancy way of saying the speed of light is the same for everyone. Every successful quantum field theory respects this symmetry. The standard model of particle physics, which describes all known fundamental particles and 3 of the 4 fundamental forces, is entirely Lorentz invariant. The speed limit isn't an add-on. It isn't a constraint imposed from outside. It's woven into the mathematical fabric of the theory from the very first line. This universality is important. The speed limit isn't just about light. It isn't just about electromagnetic waves. It applies to everything. Gravity, the strong nuclear force, the weak nuclear force, all interactions between particles, all exchanges of energy and information. Everything in the physical universe respects this one limit. And the reason is that everything exists within space-time. and space-time as a geometry that demands it. There's something profound here that's worth pausing to appreciate. The speed of light, this number we measure with lasers and atomic clocks, isn't really about light at all. It's about the shape of reality. It's a geometric property of the four-dimensional fabric that underlies everything. Light happens to travel at this speed because light is massless and must therefore move along the boundary between time-like and space-like paths. But the boundary would exist even without light. The speed limit would exist even in a universe with no electromagnetic radiation at all. The universe would still have its maximum speed, its conversion factor between space and time, its geometric constraint on how fast causes can produce effects. This is what makes the speed of light different from every other speed in physics. The speed of sound in air, about 343 meters per second, is a property of air. Change the temperature, change the medium, and the speed of sound changes. It's a property of the material, not a property of the universe. But the speed of light in a vacuum is a property of the universe. You can't change it by changing conditions. There's no dial to turn, no knob to adjust. It's baked into the geometry of space-time itself. It's as fundamental as the number of dimensions we live in. You might as well ask why space has 3 dimensions, or why time moves in one direction. These aren't choices the universe made. They're properties of its structure. Hermann Minkowski, Einstein's former mathematics professor at the Swiss Federal Polytechnic, was the one who most clearly articulated this geometric understanding. In 1908, Minkowski gave a famous lecture in which he declared that space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Minkowski had realized that Einstein's theory of special relativity was really a theory of geometry. These strange effects of relativity, time dilation, length contraction, the relativity of simultaneity, weren't mysterious or paradoxical. They were simply what happens when you rotate your direction of motion in a 4-dimensional space with a particular kind of geometry. Think of it this way. In ordinary 3-dimensional space, if you take a stick and rotate it, its shadow on the wall changes length. If you hold the stick parallel to the wall, the shadow is as long as the stick. But if you rotate the stick so it points partly away from the wall, the shadow gets shorter. The stick itself hasn't changed length. You've just rotated it so that less of its length is projected onto the wall. Length contraction in relativity works the same way. When an object moves relative to you, it appears shorter in the direction of motion. Not because the object has physically shrunk, but because you're seeing a different projection of it in space-time. Its 4-dimensional length is the same, but because you and the object are moving relative to each other, you see a different 3-dimensional slice of it. You see a shorter shadow. Time dilation is the same kind of thing. When an object moves relative to you, its clocks appear to run slowly. Not because the clocks are broken, but because you're seeing a different temporal projection of the object's motion through space-time. The object's total speed through space-time hasn't changed. It's still moving at the speed of light through space-time. But some of that motion has been rotated from the time direction into the space direction. So less of it projects onto time. The clock ticks more slowly, because less of the object's space-time motion is in the time direction. All the seemingly paradoxical effects of special relativity dissolve when you understand them as geometry. They're not strange. They're not paradoxical. They're just projections, shadows, different views of the same four-dimensional reality seen from different angles. And the speed limit, the fact that nothing can travel faster than light, is the most fundamental geometric fact of all. It's the fact that space-time has a particular shape, a particular structure, a particular kind of geometry that distinguishes time from space and imposes a maximum on how fast spatial motion can be. So when someone asks why the universe has a speed limit, the deepest answer is this: the universe has a speed limit because space-time has geometry. Not the ordinary geometry of flat space where all directions are equivalent, but a special kind of geometry where time and space are different, where they combine with a minus sign, where there's a natural boundary between time-like and space-like paths. The speed of light sits on that boundary. It's the maximum speed at which anything can travel through space, because it represents the complete conversion of temporal motion into spatial motion. Beyond that, there's nowhere to go. Not because of a wall or a barrier, but because the geometry of space-time simply doesn't allow it. There is no faster, just as there is no norther than the North Pole. This understanding changes how you should think about the speed limit. It's not a frustrating restriction like a speed trap on a highway. It's not something imposed from outside that prevents us from going faster. It's a feature of the universe's architecture. It's the shape of reality. And as we're about to see, this shape has consequences that go far beyond just how fast things can travel. It determines how energy and mass are related. It explains why accelerating to the speed of light requires infinite energy. And it reveals one of the most famous equations in all of science. Because the speed limit isn't just a limit on speed, it's a window into the deepest relationship between matter, energy, and the structure of the cosmos. Now that we understand where the speed limit comes from, let's explore what actually happens when objects approach it. Because the geometry of space-time doesn't just set a maximum speed. It reshapes everything about how objects behave as they get closer and closer to that maximum. And the effects are not subtle. They are dramatic, measurable, and confirmed by over a century of experiments. They change how time flows, how distances appear, how mass behaves, and how energy works. And they lead directly to the most famous equation in all of science. Let's start with time dilation, because this is the effect people find most unsettling, and it's also the one that's been most thoroughly confirmed by experiment. We touched on this earlier when we talked about the light clock on the train. But now let's look at what actually happens as you go faster and faster, approaching the speed of light. At everyday speeds, time dilation is negligible. If you're walking at 5 kilometers per hour, time for you is passing at essentially the same rate as time for someone standing still. The difference is so small that it would take billions of years for the discrepancy to add up to even 1 second. At highway speeds, it's still negligible. If you drive at 100 kilometers per hour for an entire year, you age about 1 billionth of a second less than someone who stayed home. Real, but completely unmeasurable by any clock you could carry in your car. At airplane speeds, the effect becomes just barely measurable. The Haffel-Keating experiment in 1971 demonstrated this. Cesium atomic clocks, the most precise timekeeping devices available at the time, were flown around the world on commercial airliners. When compared to identical clocks that stayed on the ground, the flying clocks had lost a few hundred nanoseconds, a few hundred billionths of a second. Tiny but real, and precisely matching the predictions of special and general relativity. This experiment was a landmark. It proved that time dilation isn't just a theoretical prediction. It's a physical fact that happens to real clocks in the real world. But at truly high speeds, speeds approaching the speed of light, the effect becomes dramatic. At 10% of the speed of light, about 30,000 kilometers per second, time passes about 0.5% slower for the moving object compared to a stationary observer. Still small, but starting to become significant. At 50% of the speed of light, time passes about 15% slower. At 90% of the speed of light, time passes about 2.3 times slower. Your clock ticks once for every 2.3 ticks of a stationary clock. At 99% of the speed of light, time passes about 7 times slower. And at 99.9% of the speed of light, time passes about 22 times slower. Notice the pattern. As you approach the speed of light, the time dilation doesn't increase steadily. It accelerates. The closer you get, the more extreme the effect becomes. Going from 0 to 50% of light speed barely doubles the time dilation factor. But going from 99% to 99.9% increases it from 7 to 22. And going from 99.9% to 99.99% would increase it even further. As you asymptotically approach the speed of light, the time dilation factor doesn't just grow, it shoots toward infinity. At exactly the speed of light, time would stop completely. The time dilation factor would be infinite. This isn't speculation. We see this every day in particle accelerators around the world. Particle accelerators routinely push subatomic particles to speeds incredibly close to the speed of light. At the Large Hadron Collider at CERN, protons are accelerated to 99.999991% of the speed of light. That's 6 nines after the decimal point. And the time dilation for these protons is enormous. From the perspective of someone in the laboratory, the proton's internal clocks are running about 7,454 times slower than normal. Processes that would normally happen in a fraction of a microsecond take thousands of times longer from our perspective because time itself is crawling for those protons. One of the most elegant confirmations of time dilation comes from something that happens naturally, without any laboratory equipment. High-energy cosmic rays, particles from deep space that slam into Earth's upper atmosphere, create a shower of secondary particles when they collide with atmospheric molecules. Among these secondary particles are muons. Muons are subatomic particles similar to electrons but about 207 times heavier. And they're unstable. They decay with a mean lifetime of about 2.2 microseconds. That means if you start with a group of muons, after 2.2 millionths of a second, half of them will have decayed into other particles. Now, muons created in the upper atmosphere are typically produced at altitudes of about 15 kilometers. They travel downward at speeds very close to the speed of light, typically about 99.8% of light speed. Here's the problem. Even traveling at 99.8% of light speed, a muon should only be able to travel about 660 meters in 2.2 microseconds. That's not even close to 15 kilometers. After traveling 660 meters, half the muons should have decayed. After another 660 meters, half of the remaining ones should have decayed. By the time the muons reach the ground, having traveled 15 kilometers, virtually none of them should be left. The number surviving should be essentially zero. But that's not what we observe. We detect enormous numbers of muons at ground level, far more than classical physics would predict. The muons are surviving their journey through the atmosphere as if they have much longer lifetimes than 2.2 microseconds. The explanation is time dilation. From our perspective on the ground, the muons are moving at 99.8% of the speed of light. At that speed, time dilation stretches their apparent lifetime by a factor of about 15. Instead of living for 2.2 microseconds, from our perspective, the muons live for about 33 microseconds. And in 33 microseconds, traveling at nearly light speed, they can cover about 10 kilometers. That's enough for a significant fraction to reach the ground. The numbers match exactly what we observe. From the muon's perspective, something different but equally valid is happening. The muon isn't experiencing time dilation. From its own frame of reference, it lives for exactly 2.2 microseconds, just as expected. But from the muon's perspective, it's the Earth that's rushing up toward it at 99.8% of the speed of light. And because of length contraction, the distance between the upper atmosphere and the ground is dramatically shortened. Instead of 15 kilometers, the muon sees the distance as only about 1 kilometer. And it can easily travel 1 kilometer in 2.2 microseconds at nearly light speed. Both explanations give the same answer. From our perspective, the muon lives longer because of time dilation. From the muon's perspective, the distance is shorter because of length contraction. These aren't different stories about different phenomena. They're the same story told from different frames of reference, and they both arise from the geometry of spacetime. Length contraction is the spatial counterpart of time dilation. Just as moving clocks run slow, moving objects are shortened in the direction of their motion. At everyday speeds, this contraction is immeasurably small. A car driving at 100 kilometers per hour is shorter by far less than the width of a single atom. But at speeds approaching light, the effect becomes dramatic. At 90% of the speed of light, an object is contracted to about 44% of its rest length. It appears less than half as long in the direction of motion. At 99%, it's contracted to about 14%. At 99.9%, to about 4.5%. As you approach the speed of light, the object shrinks towards zero length in the direction of motion. At exactly the speed of light, it would have zero length. Again, this isn't an optical illusion. The object doesn't just look shorter, it genuinely occupies less space in the direction of motion as measured by a stationary observer. The atoms that make up the object are closer together. The distances between them have actually decreased. From the object's own frame of reference, nothing has changed. Everything looks normal. It's the outside world that appears contracted. But from the outside, the moving object is compressed like an accordion being squeezed. Now let's talk about what happens to energy as you try to push something closer and closer to the speed of light. Because this is where the speed limit makes itself felt most forcefully. In Newtonian mechanics, accelerating an object is straightforward. You apply a force, and the object speeds up. The relationship between force and acceleration is simple. Force equals mass times acceleration. If you keep applying the same force, the object keeps accelerating at the same rate. You can, in principle, accelerate it to any speed you want. There's no upper limit. You just need enough force applied for enough time. But this picture breaks down completely at relativistic speeds. As an object approaches the speed of light, it becomes harder and harder to accelerate. Not because of friction, not because of air resistance, not because of any external force resisting the motion. It becomes harder because the object's effective resistance to acceleration increases. In relativistic physics, the energy you pump into an object trying to make it go faster doesn't all go into increasing its speed. Instead, more and more of that energy goes into increasing what physicists call the object's relativistic mass, or more precisely, its relativistic momentum and energy. Think of it this way. At low speeds, when you push something, most of the energy goes into making it move faster. But as the object approaches the speed of light, the energy starts going elsewhere. It goes into increasing the object's inertia, its resistance to further acceleration. The object becomes, in effect, heavier. Not because you've added atoms to it, not because anything physical has been attached to it, but because the geometry of space-time dictates that the relationship between energy and velocity changes as you approach the speed limit. Energy that used to buy you speed now buys you inertia. At 50% of the speed of light, an object has about 15% more energy than its rest energy. At 90%, it has about 2.3 times its rest energy. At 99%, about 7 times. At 99.9%, about 22 times. And as you approach the speed of light, the energy required doesn't just increase, it goes to infinity. This is not a gradual increase that might eventually level off. The energy required to accelerate an object to the speed of light is literally infinite. Not very large, not astronomically huge, infinite. No finite amount of energy, no matter how large, would be sufficient. You could harness the energy output of every star in the observable universe, and it still wouldn't be enough to accelerate a single grain of sand to the speed of light. Not because you'd run out of energy before you got there, but because the energy requirement is infinite. There is no amount of energy that would do it. Particle accelerators demonstrate this daily. At the Large Hadron Collider, protons are accelerated using enormous amounts of energy. The machine consumes about 1.3 terawatt hours of electricity per year, roughly the same as a medium-sized city. All that energy accelerates protons to 99.999991% of the speed of light. That's extraordinarily close to light speed, but not quite there. And to close that final tiny gap, to go from 99.999991% to 100% would require more energy than exists in the entire observable universe. The gap between almost the speed of light and exactly the speed of light is infinitely wide in terms of energy. This is where Einstein's famous equation comes in. E equals mc squared. This is probably the most famous equation in all of science, but most people don't realize what it's really saying, and even fewer realize that it's a direct consequence of the speed limit. The equation says that energy equals mass times the speed of light squared. But what does that actually mean? It means that mass and energy are the same thing expressed in different units. Mass is a form of energy. Energy is a form of mass. They're interchangeable, and the speed of light squared is the conversion factor between them. Think back to what we discussed about the speed of light being a conversion factor between space and time. E equals mc squared is the same idea applied to mass and energy. Just as the speed of light tells you how much space corresponds to how much time, the speed of light squared tells you how much energy corresponds to how much mass. And because the speed of light is a very large number, the speed of light squared is an astronomically large number, about 90 quadrillion in metric units. This means that a tiny amount of mass corresponds to an enormous amount of energy. 1 kilogram of matter, if converted entirely to energy, would release about 90 quadrillion joules. That's roughly the energy of a 21 megaton nuclear explosion. 21 million tons of TNT from 1 kilogram of mass. Not from 1 kilogram of uranium or plutonium, from 1 kilogram of anything. A kilogram of water, a kilogram of air, a kilogram of cheese. The energy is in the mass itself, not in the chemical or nuclear bonds. Every piece of matter contains this enormous reservoir of energy, locked up in its very existence. This isn't theoretical. Nuclear reactions tap into this energy. In nuclear fission, used in nuclear power plants and atomic bombs, heavy atoms like uranium split into lighter fragments. The total mass of the fragments is slightly less than the mass of the original uranium atom. That tiny difference in mass is converted into energy according to E equals mc squared. The amount of mass converted is minuscule, less than 1% of the total. But because the conversion factor is so enormous, the energy released is tremendous. In nuclear fusion, the process that powers stars, light atoms like hydrogen, fuse together to form heavier atoms like helium. Again, the total mass of the products is slightly less than the mass of the ingredients. That missing mass becomes energy. The sun converts about 4 million tons of matter into energy every single second through this process. 4 million tons of mass simply ceasing to exist and becoming energy every second. And it has been doing this for 4.5 billion years. That's how much energy is locked up in mass. Now, here's the connection to the speed limit. E equals mc squared isn't just a random equation that happens to relate mass and energy. It's a necessary consequence of the fact that the speed of light is the same for all observers. Einstein derived it directly from the postulates of special relativity. If the speed of light is the same for everyone, and if the laws of physics are the same for everyone, then mass must be equivalent to energy with c squared as the conversion factor. The equation isn't independent of the speed limit. It's a product of it. Without the speed limit, without the constancy of the speed of light, E equals mc squared wouldn't exist. The reason accelerating to the speed of light requires infinite energy is now clear. As you accelerate an object, you're adding energy to it. That energy, according to E equals mc squared, has mass. So the object effectively becomes more massive. A more massive object is harder to accelerate. So you need even more energy to keep accelerating it. But the additional energy also has mass, making the object even harder to accelerate. You're caught in a feedback loop. Every bit of energy you add to speed the object up also makes it harder to speed up further. As you approach the speed of light, this feedback loop runs away. The energy required increases without bound, the effective mass increases without bound, and you can never quite reach light speed. You get closer and closer, asymptotically approaching it, but never arriving. This is why the speed limit isn't a technological challenge. It's not that our engines aren't powerful enough. It's not that we need a better power source or a cleverer propulsion system. The geometry of space-time makes it mathematically impossible for anything with mass to reach the speed of light. It would require infinite energy, and infinite energy doesn't exist. This is as absolute as a mathematical proof. There's no loophole, no workaround, no trick. It's like asking someone to draw a square circle. It's not that they're not talented enough. The request is self-contradictory. It can't be done, not because of any limitation on ability, but because of the structure of the concepts involved. Now, what about massless particles? Photons, the particles that make up light, have zero rest mass. They don't face the infinite energy problem because they never need to be accelerated to the speed of light. They're born at the speed of light. From the moment a photon is created to the moment it's absorbed, it travels at exactly the speed of light. It never goes faster. It never goes slower. It always moves at exactly c. This isn't a choice the photon makes. It's a requirement imposed by the geometry of spacetime. A massless particle must travel at the speed of light. It cannot do otherwise. Why must massless particles travel at exactly the speed of light? Because of the space-time geometry we discussed earlier. Everything moves through space-time at the speed of light. For a massive object, most of that motion is through time, with a little bit through space. As the object speeds up, more motion shifts from time to space, but the object can never shift all of its motion to space because that would mean zero motion through time, which requires zero rest mass. A massless particle, however, has no rest mass. It has no obligation to move through time at all, and so all of its space-time motion goes through space. It moves through space at the speed of light and through time, not at all. From a photon's frame of reference, time doesn't pass. The photon exists in an eternal present. Its creation and its destruction happen at the same instant from its own perspective, regardless of how far it travels in our frame of reference. This means that if you could somehow give a photon mass, even the tiniest amount, it would immediately slow down below the speed of light. And if you could somehow remove all mass from an electron, it would immediately jump to the speed of light. The speed of light is the natural speed of massless things. Mass is what slows things down below light speed. In a deep sense, the question isn't why there's a speed limit. The question is why things go slower than light at all. And the answer is mass. Mass is what drags you below the universe's natural speed. Without mass, everything would travel at the speed of light. There's another consequence of the speed limit that's worth understanding, and it has to do with the relationship between energy and momentum at relativistic speeds. In Newtonian physics, the kinetic energy of an object, its energy of motion, increases with the square of its velocity. Double the speed, quadruple the energy. This works well at low speeds, but at relativistic speeds, this relationship breaks down. The kinetic energy of an object approaching the speed of light increases much faster than the square of its velocity. It increases without bound, asymptotically approaching infinity as the speed approaches c. This has practical implications. At the Large Hadron Collider, the protons circulating in the beam each have about the same kinetic energy as a flying mosquito. That might not sound like much, but remember that a proton is trillions of times less massive than a mosquito. The fact that a single proton can have the same kinetic energy as an entire mosquito illustrates how dramatically energy increases at relativistic speeds. Each proton, despite being inconceivably tiny, is carrying enormous energy because it's moving at 99.999991% of the speed of light. And when two such protons collide head-on, their combined energy is enough to create entirely new particles. Particles far more massive than the protons themselves. This is how the Higgs boson was discovered in 2012. Two protons, each carrying enormous kinetic energy, collided, and the energy of their collision was converted into mass, creating a Higgs boson that's about 133 times more massive than a proton. Energy became mass. E equals mc squared running in reverse. This process of creating particles from energy is one of the most dramatic consequences of the speed limit and the mass-energy equivalence it implies. In particle accelerators, physicists routinely create new particles by smashing existing particles together at enormous energies. The energy of the collision is converted into mass, producing particles that weren't there before. This is how antimatter is produced. This is how exotic particles like the top quark, the heaviest known fundamental particle, are created. Top quarks have a mass about 184 times that of a proton. They don't exist in ordinary matter. They can only be created by concentrating enough energy in a small enough space, which requires collisions at speeds incredibly close to the speed of light. The universe itself used this process in its earliest moments. In the first fraction of a second after the Big Bang, the universe was filled with energy so intense that particles and antiparticles were constantly being created and annihilated. Matter and antimatter popping in and out of existence, energy becoming mass and mass becoming energy in a constant frenzy. As the universe expanded and cooled, this process slowed and eventually stopped. But for a brief time, E equals mc squared was the dominant process in the universe, creating all the matter that would eventually form stars, planets, and us. Let me bring this all together. The speed limit, the fact that nothing can travel faster than light, is a geometric property of spacetime. It's not imposed from outside. It's built into the structure of reality, and it has consequences that reach into every corner of physics. Time dilation, the slowing of time for moving objects, is a geometric consequence of the speed limit. It's been confirmed by experiments ranging from atomic clocks on airplanes to muons in the atmosphere to protons in particle accelerators. Length contraction, the shortening of objects in the direction of motion, is another geometric consequence. It's the spatial counterpart of time dilation, and it explains why muons can survive their journey through the atmosphere. The relativistic increase in energy required for acceleration is yet another consequence. As objects approach the speed of light, they require ever-increasing amounts of energy to accelerate further, with the required energy going to infinity at light speed. This makes reaching the speed of light impossible for anything with mass, and E equals mc squared, the equivalence of mass and energy, is a direct product of the speed limit. It tells us that mass is concentrated energy, that the two are interchangeable, and that the conversion factor between them is determined by the same constant that defines the speed limit. All of these effects, time dilation, length contraction, the energy barrier, mass energy equivalence, are not separate phenomena. They're all aspects of the same underlying reality. They're all consequences of the geometry of space-time. They're all reflections of the fact that space and time are unified, that there's a maximum speed built into that unification, and that this maximum speed is a structural feature of the universe, not a rule imposed from outside. The evidence for all of this is overwhelming. Time dilation has been measured with atomic clocks, with muons, with particles and accelerators, with GPS satellites. Length contraction is confirmed every time muons reach the ground. The energy barrier is demonstrated every day at particle accelerators around the world. Mass energy equivalence powers nuclear reactors, explains how stars shine, and creates new particles in collider experiments. These aren't fringe claims or untested theories. They're among the most thoroughly confirmed facts in all of science, verified by thousands of independent experiments over more than a century, and all of it flows from one simple fact. The speed of light is the same for every observer. From that single statement, the entire edifice follows. Time dilation, length contraction, the energy barrier, E equals mc squared, everything. One fact about the speed of light and the entire structure of modern physics unfolds from it like a flower from a seed. That's the power of the speed limit. It's not just a number. It's not just a restriction on how fast you can go. It's the key that unlocks the deepest structure of reality, the thread that connects space and time, mass and energy, cause and effect into a single unified tapestry. But that thread runs deeper still, because the speed limit doesn't just determine how objects move through space-time. It determines the very structure of cause and effect. It determines what can influence what. It determines the difference between past and future. And it's the reason the universe has a coherent history at all. Everything we've discussed so far, time dilation, length contraction, the energy barrier, mass energy equivalence, these are all remarkable consequences of the speed limit. But none of them is the deepest reason the speed limit matters. The deepest reason is something more fundamental than any of these effects. The speed limit is what makes cause and effect possible. It is the reason the universe has a coherent story. Without it, reality as we know it would not merely be different. It would be incoherent. It would be nonsensical. It would collapse into paradox. To understand why, we need to talk about something called a light cone. And to understand light cones, we need to think carefully about what it means for one event to cause another. In your everyday life, causality seems obvious. You knock a glass off a table, and it shatters on the floor. The knock caused the shattering. The cause came first. The effect came second. The order is absolute and unambiguous. Nobody disputes which happened first. Nobody claims the glass shattered before you knocked it. Causes precede their effects. Always. This seems like such a basic feature of reality that most people never even think about it. Of course, causes come before effects. How could it be otherwise? But here's the thing that special relativity reveals. The order of events in time is not always the same for all observers. We talked about this earlier. Two events that are simultaneous for one observer might happen at different times for another observer moving at a different speed. This is called the relativity of simultaneity, and it's one of the strangest consequences of the speed limit. Different observers, moving at different velocities, literally disagree about the order in which events happen. This immediately raises a terrifying question. If different observers can disagree about the order of events, does that mean they can disagree about which came first, the cause or the effect? Could one observer see you knock the glass off the table and then see it shatter, while another observer, moving at a different speed, sees the glass shatter first and then sees you knock it? Could the order of cause and effect be reversed depending on who's watching? The answer, thank goodness, is no. And the reason is the speed limit. The speed limit protects causality. It ensures that while observers can disagree about the order of some events, they can never disagree about the order of causally connected events. If event A causes event B, then every observer in the universe, regardless of their speed or direction of motion, will agree that A happened before B. No one will ever see the effect before the cause. The causal order is preserved for everyone, everywhere, always. How does the speed limit accomplish this? Through the geometry of light cones. Imagine an event, any event, a firecracker going off, a star exploding, a photon being emitted, anything that happens at a specific place and a specific time. Now imagine that at the moment this event occurs, light begins spreading outward from it in all directions. Since light is the fastest thing in the universe, this expanding sphere of light represents the absolute limit of how far the event's influence can reach over time. 1 second after the event, the light has traveled 300,000 kilometers in every direction. 1 year after the event, the light has traveled 1 light year. 1 billion years after the event, the light has traveled 1 billion light years. If you draw this on a space-time diagram, with time going upward and space going outward in all directions, the expanding sphere of light traces out a cone shape. This is the future light cone of the event. Everything inside this cone, every point in space-time that the light can reach, is within the event's sphere of possible influence. The event can send a signal there. It can cause something to happen there. It can affect things there. Everything outside the cone, every point that the light hasn't reached yet, is beyond the event's influence. The event cannot affect those regions. No signal, no force, no influence of any kind from the event can reach those points, because doing so would require something to travel faster than light. There's also a past light cone. This is the cone that opens downward in the space-time diagram, representing all the events in the past that could have influenced the original event. These are all the points in space-time from which a light signal could have reached the event's location by the time it occurred. Anything inside the past light cone could have caused the event. Anything outside the past light cone could not have, because a signal from those regions would have needed to travel faster than light to arrive in time. The light cones divide all of space-time into 3 distinct regions relative to any given event. First, the interior of the future light cone. These are all the events that the original event can potentially influence. Physicists call this region the absolute future of the event. Second, the interior of the past light cone. These are all the events that could potentially have influenced the original event. This is the absolute past. Third, everything outside both cones. This is the region that the event cannot influence and that cannot have influenced the event. No causal connection is possible. Physicists call this region space-like separated or elsewhere. Here's the crucial point. For events inside each other's light cones, the order of events is absolute. Every observer agrees on which one happened first. If event A is in event B's past light cone, then A happened before B according to every observer in the universe, no matter how they're moving. You cannot find any frame of reference in which the order is reversed, because always comes before effect for causally connected events. The light cone structure of space-time guarantees this. For events outside each other's light cones, the situation is different. These events are space-like separated. They cannot influence each other because no signal, not even light, could travel between them in time. And for these events, different observers can genuinely disagree about the order. One observer might say event A happened first. Another might say event B happened first. A third might say they happened simultaneously. All 3 are equally correct. But this disagreement doesn't threaten causality because these events can't influence each other anyway. It doesn't matter which one you think happened first because neither one caused the other. They're completely independent events that happen to occur in different parts of the universe, with no causal connection between them. Disagreeing about their order is harmless. It's like two people disagreeing about whether a tree fell in Brazil before or after a rock fell in Japan when neither event had anything to do with the other. Who cares about the order? The events are unrelated. The speed limit is what makes this elegant structure possible. By ensuring that no information can travel faster than light, the speed limit ensures that every cause and effect relationship falls within the light cone structure. Every cause is in the past light cone of its effect. Every effect is in the future light cone of its cause. And within light cones, the temporal order is absolute and agreed upon by everyone. Now, here's where things get really interesting. What would happen if the speed limit could be violated? What if something could travel faster than light? The answer is that causality would break. Not in some subtle academic way. In a complete, devastating, reality-destroying way. If you could send a signal faster than light, you could send it to a point outside your future light cone. A point that's space-like separated from you. And we just said that for space-like separated events, different observers disagree about the order. This means that if you send a faster than light signal, there exists some observer, moving at some perfectly ordinary sublight speed, who would see the signal arrive before it was sent. From their perspective, the reply would precede the question. The effect would come before the cause. Let me walk through this more carefully because it sounds like it should be impossible, but it follows directly and inescapably from the geometry of spacetime. Imagine you have a device that can send signals at twice the speed of light. You're on Earth, and your friend is on a space station 4 light years away. You send your faster than light signal. Traveling at twice light speed, it reaches your friend in 2 years. Your friend receives the message and immediately sends a reply, also at twice the speed of light. But your friend's space station is moving relative to you. Because of the relativity of simultaneity, what counts as now for your friend is different from what counts as now for you. The reply, traveling at twice light speed in your friend's frame of reference, can end up arriving back at Earth before you originally sent your message. You receive a reply to a message you haven't sent yet. You read the reply, and it tells you what your message will say, but you haven't composed that message. You haven't even decided to send it. The effect, the reply, has arrived before the cause, your original message. Causality is broken. This isn't a contrived paradox dreamed up by a philosopher. It's a mathematical certainty that follows directly from the postulates of special relativity. If faster than light communication is possible, then communication backward in time is also possible. There's no way to have one without the other. The geometry of space-time, the same geometry that gives us time dilation and length contraction and E equals mc squared, absolutely guarantees that faster than light signals can be rearranged into backward in time signals by choosing the right reference frame. And backward in time communication creates paradoxes that destroy logical consistency. The most famous is the grandfather paradox. If you can send information backward in time, you can send a message that prevents the cause of that very message. You could tell yourself not to send the message, but if you don't send the message, then you never receive the instruction not to send it. So you send it after all, which means you receive the instruction not to send it, which means you don't. Around and around forever. The situation is logically incoherent. It has no consistent solution. The speed limit prevents all of this. By ensuring that no signal can travel faster than light, the speed limit ensures that no signal can escape its sender's future light cone. And within light cones, temporal order is absolute. Causes always come before effects. Paradoxes cannot arise. The universe maintains logical consistency. This is the deepest role of the speed limit. Deeper than time dilation. Deeper than E equals mc squared. The speed limit is the guardian of causality. It's the reason the universe makes sense. It's the reason events have a coherent order. It's the reason the past is different from the future. It's the reason you can make decisions that affect what happens next, rather than living in a universe where the future reaches back and changes the past. Without the speed limit, the word because would have no meaning. Effects could precede causes. Consequences could come before actions. The entire logical structure of reality would unravel. Now, I want to address something that confuses a lot of people. The expansion of the universe. You may have heard that distant galaxies are receding from us faster than the speed of light. This is true. Galaxies sufficiently far away are moving away from us at speeds that exceed the speed of light. And this seems like it should violate everything we've discussed. How can galaxies move faster than light if the speed of light is the absolute maximum speed? The answer is that these galaxies aren't moving through space faster than light. Space itself is expanding, carrying the galaxies with it. The galaxies are sitting relatively still in their local region of space, like raisins in raising bread dough. Each raisin isn't moving through the dough itself is stretching, increasing the distance between raisins. Two raisins far enough apart will see the distance between them growing faster than any speed the raisins themselves could achieve, because the expansion is cumulative. Every bit of dough between them is stretching a little, and the total stretching over a large distance can add up to an enormous rate of separation. This doesn't violate the speed limit because the speed limit applies to objects moving through space, not to space itself expanding. No galaxy is traveling through its local space faster than light. No information is being transmitted faster than light. No causal signal is being sent faster than light. The galaxies are simply being carried apart by the expansion of the fabric in which they sit. The speed limit governs motion within spacetime. The expansion of spacetime itself is a different thing entirely. This distinction has real consequences. Galaxies that are receding from us faster than light are beyond our cosmic event horizon. Light from those galaxies will never reach us because the space between us and them is expanding faster than light can cross it. We can never see them, never communicate with them, never learn anything about them. They are permanently and irrevocably beyond our reach. Not because they're moving too fast through space, but because space itself is growing too quickly between us and them. The speed limit is respected locally, everywhere, at every point in space. But the cumulative effect of cosmic expansion can separate regions of space faster than light can traverse them. This is one of the most profound consequences of the speed limit applied to cosmology. The observable universe, the part of the cosmos we can actually see, has a boundary. Not a physical edge, but a causal boundary. A horizon beyond which events cannot influence us, and we cannot influence them. This horizon exists precisely because of the speed limit. Light from beyond the horizon hasn't had time to reach us given the age of the universe and the rate at which space is expanding. We live inside a bubble of causal contact, roughly 93 billion light years across, and everything beyond that bubble is forever hidden from us. Now, what about proposed ideas for getting around the speed limit? Warp drives, wormholes, and other science fiction concepts. Let's examine them in light of what we now understand about causality. The Alcubierre warp drive, proposed by physicist Miguel Alcubierre in 1994, is a theoretical solution to Einstein's field equations of general relativity. It describes a bubble of warped space-time that contracts space in front of a spacecraft and expands it behind, effectively moving the bubble and the spacecraft inside it faster than light. The spacecraft itself doesn't move through local space faster than light. The space around it is being manipulated. This sounds like it might avoid the speed limit in the same way that cosmic expansion does. But there's a critical difference. The expanding universe doesn't transmit information faster than light. Distant galaxies receding from us faster than light can't send us messages, and we can't send messages to them. The recession creates a horizon, cutting off causal contact. A warp drive, on the other hand, is designed specifically to transmit something faster than light, namely the spacecraft and everyone on it, from one point in space to another. This is precisely the kind of faster than light transmission that, as we discussed, can be rearranged into backward in time travel using the right reference frame. If you could build a working warp drive, you could use two of them moving in different directions to create a closed time-like curve, a path through space-time that returns to its own past. You could send a ship on a round trip that arrives before it left. Every paradox we discussed, the grandfather paradox, the logical inconsistencies, all of them become possible. This isn't a minor technical problem, it's a fundamental conflict with the causal structure of space-time. And the problems don't stop there. The Alcubierre drive requires exotic matter with negative energy density to function. No such matter is known to exist. Some physicists believe that quantum mechanics might allow negative energy in certain configurations, but the amounts required are astronomical, possibly exceeding the total energy of the observable universe. There are also arguments from quantum field theory suggesting that any attempt to create a warp bubble would result in devastating radiation that would destroy anything inside the bubble and anything the bubble approached. Wormholes face similar problems. A wormhole is a hypothetical tunnel through space-time connecting two distant points. If wormholes exist and could be traversed, they could potentially allow faster than light travel, at least from the perspective of someone taking the long way around through ordinary space. But like warp drives, traversable wormholes could be used to create closed time-like curves, paths that loop back to their own past. And they face the same problem with exotic matter. Keeping a wormhole open long enough for anything to pass through it would require negative energy in enormous quantities. Without exotic matter, any wormhole would collapse before anything could cross it. There's a deeper point here that goes beyond the specific technical problems of warp drives and wormholes. The recurring theme is causality. Every proposed mechanism for faster than light travel, when analysed carefully, either violates causality or requires conditions that appear to be physically impossible, or both. This pattern is not a coincidence. It reflects something fundamental about the structure of space-time. The speed limit and causality are not separate features. They're the same feature. The speed limit exists because causality requires it. Any mechanism that circumvents the speed limit automatically threatens causality. And causality is not optional. Without it, the universe doesn't function as a coherent reality. Some physicists have speculated about the possibility that the universe might simply prevent paradoxes from arising, even if faster than light travel were possible. This is called the Novikov self-consistency principle. It suggests that the laws of physics conspire to prevent paradoxes, allowing only self-consistent solutions. You could go back in time, but you couldn't change anything. Every action you took in the past would turn out to be part of the history that already happened. But this principle, while interesting, is speculative. We have no evidence that the universe works this way, and most physicists regard the simpler explanation as more likely. Faster than light travel is simply not possible because the geometry of space-time forbids it. Let me bring all of this back to where we started. The universe has a speed limit. That speed limit is the speed of light, approximately 299,792 kilometers per second. But as we've seen, calling it a speed limit doesn't really capture what it is. It's not a speed limit in the way a highway has a speed limit, an arbitrary rule that could be set to a different value. It's a structural feature of space-time geometry, like the number of dimensions or the curvature of space around massive objects. It exists because space-time has a particular kind of geometry, a geometry in which space and time are unified but distinct, in which there's a natural boundary between time-like and space-like paths, and in which that boundary imposes a maximum on how fast any influence can propagate. The speed of light is really the speed of causality. It's the rate at which the universe updates itself. It's the maximum speed at which a cause can produce an effect. It's the thread that holds together the logical structure of reality, ensuring that the past determines the future rather than the other way around. And here's what I find most remarkable about all of this. This single constant, this one number, shapes essentially everything about the universe we live in. It determines the relationship between space and time. It determines how mass and energy are related through E equals mc squared. It determines the strength of the energy barrier that prevents massive objects from reaching light speed. It determines the structure of light cones, which in turn determines the structure of causality, which in turn determines the logical coherence of reality. It determines the size of atoms, because the electromagnetic interactions that govern atomic structure propagate at the speed of light. It determines the size of the observable universe, because the cosmic horizon is set by how far light has traveled since the Big Bang. It determines the fate of the cosmos, because the interplay between cosmic expansion and the speed of light dictates which regions of the universe can remain in causal contact, and which will be forever separated. One constant, one number. And from it, the entire architecture of physical reality follows. This speed limit also shapes our relationship with the cosmos in ways that are both sobering and beautiful. Because light travels at a finite speed, when you look at a distant star, you're seeing it as it was years ago. The further away you look, the further back in time you see. Looking out into space is literally looking back through time. The most distant galaxies we can observe with telescopes like the James Webb Space Telescope appear to us as they were over 13 billion years ago, not long after the Big Bang itself. The speed of light turns the universe into a time machine, one that works only in one direction, letting us see the past, but never touch it. The speed limit also means that humanity is profoundly isolated. The nearest star is over 4 light years away. Even traveling at an appreciable fraction of the speed of light, reaching it would take years or decades. Most stars in our galaxy are thousands of light years away. Other galaxies are millions or billions of light years away. The distances are so vast and the speed limit so absolute that meaningful contact with other civilizations, if they exist, might be impossible. We might share a universe with billions of intelligent species and never know it, because the speed of light makes the cosmos too vast for signals to cross in time. But the speed limit also makes the universe beautiful. It gives us the night sky. When you look up at the stars, you're seeing light that has traveled for years, decades, centuries, sometimes millennia to reach your eyes. Each photon has been crossing the void of space at 300,000 kilometers per second, faithfully carrying its tiny packet of information about a distant star, for a journey that might span centuries. And now that photon ends its journey by entering your eye, triggering a nerve impulse, creating the experience of seeing a star, you're connected to that distant sun by a chain of causality that stretches across light years. The photon left the star and traveled in a straight line through space-time, respecting the speed limit every step of the way until it reached you. That connection, that thread of light stretching across the darkness, exists because of the speed limit. The speed limit is what makes light travel at a finite speed. And that finite speed is what gives the universe a history you can see. The speed limit is also the reason the universe has a history at all. Without it, without the finite propagation speed for causes and effects, everything would happen at once. There would be no before and after, no past and future, no sequence of events, no evolution, no stars forming and burning and dying, no planets cooling and life arising, no species evolving and growing and wondering about their place in the cosmos. The speed limit is what gives the universe time. It's what separates now from then. It's what allows the universe to unfold, to develop, to evolve, to tell its story over 13.8 billion years of cosmic history. Without the speed limit, there would be no story, no narrative arc, no beginning, middle, and future. Just a static, timeless, everything happening at once chaos in which cause and effect have no meaning, and history doesn't exist. The speed limit is not a prison. It's the opposite. It's the condition that makes everything possible. It's the reason the universe has structure, has history, has order. It's the reason atoms can form, stars can shine, planets can cool, life can emerge, minds can wander. Every moment of your existence, every thought you've ever had, every experience you've ever lived, all of it is possible because the universe has a speed limit. Because causes precede effects. Because the past is different from the future. Because space-time has the geometry it has, with a maximum speed built into its very fabric. So the next time someone tells you that nothing can travel faster than the speed of light, remember that this isn't a frustrating restriction. It isn't a cosmic speed trap. It isn't a wall that blocks our ambitions or a cage that traps us in our corner of the galaxy. It's the architecture of reality itself. It's the reason reality is real. It's the reason time flows, causes produce effects, and the universe has a coherent story to tell. The speed of light is not just the fastest speed. It's the speed at which the universe holds itself together. It's the heartbeat of space-time, the pulse of causality, the rhythm that gives the cosmos its order and its history and its meaning. You exist because the universe has a speed limit. Your thoughts are possible because causes precede effects. The stars shine because energy propagates at a finite speed. The night sky is beautiful because light takes time to travel across the darkness, connecting you to distant suns across years and centuries and millennia. The universe has a speed limit, and that speed limit is the reason there's a universe to have one.